am indeed excited to be here sharing this material with you. This has been sort of my research and my teaching passion for the past 10 years. So I love talking about Bayes and getting into the details on this. So basically, Bayesianism is a really beautiful framework, very beautiful and intuitive framework that is going to help us reason more rationally in a wide range of different contexts, including but hardly limited to social science. So the idea is that the way that we intuitively approach case studies or other kinds of qualitative research is going to be similar to how we would read a detective novel. Okay. So we want to figure out who done it, whether that is who killed Samuel Ratchet on the Orient Express, or maybe you are interested in how did democratization come about in South Africa. We're going to consider different hypotheses along the way, drawing on the literature that we've read and our own imagination. And as we gather evidence or as we discover clues, we are going to sort of revise our views about which of these alternative explanations, provides the best explanation for whatever it is that we're trying to understand. So Bayesianism gives us a framework to govern how we should update our initial views about which hypothesis is more plausible as we learn new information during our research. So let me give you an example. I'm, as you know, a political scientist, so I'll give you a number of different kinds of examples. But to start out, I was trained as a Latin Americanist. And if you know a little bit about Latin America, this region went through a really severe economic crisis in the 1980s and the 1990s. It was known as the debt crisis. And basically, the economies of Latin America were just a mess. You had negative growth, you had hyperinflation, things were really bad. Okay. So during this period, there was an interesting phenomenon of presidential candidates who explicitly promised the voters that they were not going to implement sort of harsh austerity measures. But then once they got elected, they actually flipped 180 degrees and they imposed very drastic neoliberal reforms. So we're talking about things like cutting consumer subsidies for food, cutting subsidies for electricity, firing public sector workers, so rapidly privatizing state industries and this kind of thing. So Susan Stokes wrote a very interesting book on this, and she considers these two rival explanations for why these presidents violated their policy mandates. So the first explanation says, well, these presidents, they were actually out first and foremost to try to represent voters' best interests. And just unlike the voters, they really believed that these economic austerity measures were going to be the only way to get their country out of this massive crisis. And then we have an alternative explanation that says, well, no, this was actually first and foremost about rent seeking. So these leaders, these presidents were just looking for ways to get kickbacks and bribes and so forth associated with privatizations and other kinds of policies that businesses that favored these reforms were pushing. So let us consider the case of President Perez in Venezuela. So he was one of these policy switchers. So let's consider the question of, well, why did he do this? Well, given whatever relevant information you know, you might strongly favor one of these two explanations. You might weakly or moderately favor one or the other, or you might just be indifferent. This is not your field. That's perfectly fine. And I'm showing you here, this is the distribution of initial views that my students had last time that I did this with a big group in my live polling technology. So you can see that I had a fairly pessimistic set of folks in that particular session. We had sort of most of the people initially on the rent-seeking side of that spectrum. Now, if I ask you to read this information, you might change your view about which of those explanations is more plausible. So according to multiple sources, President Perez learned how bad the economy was only after he took office. And he sort of noticed over the initial years that the economic policies that his colleague, President Garcia, was implementing in Peru really were not fixing the situation there. Okay. And then here you can see how people's views changed after they learned those two pieces of information. So we got a pretty significant shift toward the representation hypothesis. Right? So this example illustrates Bayesian reasoning. And here are sort of the five basic steps that I will be taking you through. So we're going to start by coming up with two or more rival hypotheses, alternative explanations to consider. We're going to assess how plausible each hypothesis is relative to the rivals, drawing on any relevant background knowledge that we have. We're going to gather evidence. We're going to ask whether the evidence fits better with one of the hypotheses relative to the rival. And then we're going to reevaluate which of these hypotheses provides the best explanation. I want to point out at any point we are free to come up with a new hypothesis or to revise a hypothesis. If that happens, we just are going to bounce back up to the step one, and then we will move through this process again. Okay. Bayes is going to tell us precisely what it means for the evidence to fit better with one hypothesis relative to a rival. So we are going to be asking which of our hypotheses makes the evidence that we find seem more expected. And I'll be saying much more about that moving forward, but let me just highlight that this is the step that's going to tell us how strongly the evidence favors one hypothesis over a rival. And then, according to Bayes' rule, we are going to gain more confidence in whichever of those hypotheses makes our evidence more expected. So why Bayes? Well, I think Bayesianism has quite a lot to offer qualitative research. Here. It's going to give us a rigorous methodological foundation for inference with qualitative evidence. And I think this is going to be a really powerful tool for improving inference in qualitative research. And my view after sort of working on methodology for quite some time is that the alternatives out there in the qualitative methods literature really sort of lack the compelling mathematical and logical foundation that Bayesianism provides. Okay. This is going to be it's going to mirror the way that we naturally approach inference, but it also helps us avoid cognitive biases that might lead to sloppy reasoning. And a prime example there is confirmation bias, where we forget to consider whether the evidence might fit equally well or even better with a rival hypothesis. And this is also a very useful framework for scrutinizing inferences and trying to build consensus. So Bayes is going to direct us to ask whether, if we disagree about an inference, is that because we have very different initial views about which hypothesis is more plausible? Or, could it be that we are just evaluating the evidence very differently, and we need to sort of sit down and have a conversation to figure out why, where our disagreement is and whose line of reasoning about the evidence is more compelling? Okay, great. So let me just take these few next minutes to sort of give you an overview of what we're going to be covering in the next couple days. So today I'm going to be giving you a basic introduction to Bayesian probability. Bayesianism conceptualizes probability as the rational degree of belief that we should hold in the truth of a proposition given the information that we possess, which is inevitably going to be limited. So Bayesianism is going to be all about reasoning under conditions of uncertainty and trying to honestly assess how much confidence your research findings merit. There are lots of sort of fun probability problems and mind twisters that Bayes helps us solve, and we're going to be looking at a few of those. And let me just sort of preview one that we're going to come back to later. So suppose we have a candy shop And the candy shop makes two different kinds of truffles. We have milk chocolate and dark chocolate, and they get just sort of randomly packaged into identical boxes. At the end of the day, there are two boxes left, and we want to know the probability that both contain dark chocolate. So chocolate is a very important part of my life. I consider it sort of one of the basic food groups of important nutritional value. And I happen to be very partial to dark chocolate. So this is sort of a very important question to me. So I want to know, at the end of the day, what is the probability that both of these two boxes have dark chocolate? Now, I've given you two different versions of the problem on the slide here. So in the first example, the shop owner tells us that the box on the left has dark chocolate in it. And then I have a different version of the problem on the bottom where the owner instead tells us, well, I looked in one of the boxes and I saw that it had dark chocolate, but I don't remember which one of the boxes it was. So in both instances, we're interested in the question of what is the probability that both of these boxes contain dark chocolate. And the puzzle here is the answer the same? Is the answer the same in each version of this problem, or is the answer different? Okay, so I'm going to let you sort of puzzle about that in the back of your head until we come back to it and talk about it later today. Once we have the basics of probability theory down, we will move on to talk about how to construct a set of alternative explanations to compare. Bayesian reasoning is about inference to best explanation. So we want to figure out which of the hypotheses that you've thought up best explains the evidence that you've gathered. We're going to talk about exactly what it means for hypotheses to be rivals. This is a point that I found, at least in my field, tends to cause quite a lot of confusion, but I think you're going to see that it's really quite straightforward. The basic idea is just that if one of the hypotheses is true, then the others must be false. And this is, we craft our hypotheses to have this property. But let me just show you, continuing with the chocolate example. So here we have two rival hypotheses. The first one proposes that both of the two boxes have dark chocolate. The rival hypothesis says at least one of those boxes has milk chocolate. And these are rival, they're mutually exclusive in that only one of them can be true, right? If both boxes have dark chocolate, then it cannot be the case that at least one of them has milk. Then we will be all set to start applying Bayesian reasoning in qualitative research. We will talk about how to assess prior odds on our hypotheses. So from the outset, how strongly do we favor one explanation over a rival? We will talk about how to identify evidence. So evidence can be really anything that bears on the truth of our alternative explanations. This can include information from interviews. A lot of you are interested in doing interviews. It could include information from news articles that you read or any kinds of archival documents that you dig up. It could include observations that you make while doing some kind of participant observation. There are really no limits whatsoever. So the idea is that you want to think of yourself as a social science detective or an anthropological detective, whatever your field is. And the goal is to go out there and get your hands on anything and everything that will help you figure out what is going on. The critical step that's going to tell us how to update our initial view about which hypothesis is more plausible is going to be asking which hypothesis makes the evidence more expected. And we'll spend quite a lot of time talking about that. This is sort of the most important, analytically most challenging as well, part of the whole process. And for this component of what I'll be showing you, we're talking or we're calling this sort of heuristic Bayesian reasoning or qualitative Bayesian reasoning, where we're applying the principles that come out of Bayesian probability to help us analyze qualitative evidence. And then what I've been calling explicit or formal Bayesian reasoning, these aren't the greatest terminology, but for lack of a better term, this is going to involve going ahead and quantifying our probabilities so that we can better communicate our inferences, and also aggregate the weight of multiple pieces of evidence more systematically. So to help us quantify our degrees of belief, we're going to be using a nice intuitive Bayesian concept called the weight of evidence. That goes back to I.J. Good and decryption efforts during World War II. So basically, every clue or every piece of evidence that we find is going to contribute some weight to our inference. And we're just going to aggregate everything up to get an overall inference that tells us how strongly the body of evidence that we have uncovered favors one hypothesis over a rival, and will give some real concrete meaning to this weighing the evidence, or this balance analogy that I've showed you visually here. Okay, so that was I advanced the introductions. Let me just have a quick check in the chat to see. Okay, so we've got a question: why put a qualitative term next to heuristic? Yeah, these terms that we came up with aren't wonderful, but again, sort of for lack of better terminology. The reason that I'm calling it qualitative Bayesian reasoning or heuristic Bayesian reasoning is because we are going to be working with plain language hypotheses and very sort of linguistic information, as opposed to a quantitative mathematical model or evidence that lends itself naturally to being quantified. So to sort of distinguish it from the more quantitative world, what we're doing, we're trying to follow the same principles, but things are going to be a little bit more hand wavy and a little bit less precise when we're in this realm where we don't have sort of mathematical models and easily quantified evidence. But there's not anything really different between these two. This basically corresponds to chapter 3 of our book. This corresponds to chapter 4 of our book. There's nothing different. It's just for what we're calling explicit or formal Bayesian reasoning, we're going to go ahead and actually quantify our degrees of belief. And I'll show you all of that probably tomorrow, but we'll see how things go with the time. Okay. So let us then go ahead and go forward. Here are the topics that I'll be covering today, and we'll just cover as much as we have time for, and then pick up where we leave off tomorrow. So let us go ahead and get started with foundations of Bayesian probability. So we are, let me got one more comment in the chat here. Okay, all good. So we're drawing on the school of probability as extended logic, which comes out of the physical sciences, out of the natural sciences. So I'm excited to have a couple of you who are also sort of in that realm. Logical Bayesianism conceptualizes probability. As I mentioned, this is the rational degree of belief that we should hold in some proposition, given whatever relevant information we possess. And that information is just inevitably going to be limited. Okay. Physicists, including James and Cox, have proved that probability theory is the unique extension of deductive logic, where we can know for certain whether our propositions are true or false, to contexts where we have uncertainty and limited information, and there's always going to be some uncertainty as to the truth values of the propositions that we're interested in. So the idea is that probability is a logical construct that's going to help us reason under these contexts of uncertainty, which we're almost always facing. This is very different from the notion of probability that underpins orthodox statistics, if you've had any exposure to conventional statistics. So there you're focusing on sort of the relative frequency of some outcome in a sequence of random trials. Okay, so for example, if you flip a coin over and over and over again ad infinitum, how many times or how often would it come up heads? So to try to really emphasize the distinctions for you, frequentism tries to view probability as an objective physical property of the world. So for the coin example, the probability of heads would be sort of objectively determined by the nature of the coin, whether it's fair or whether it's weighted. and then the nature of the flipping process, right? So is it random or is it rigged? In contrast, Bayesianism treats probability as a logical construct that's going to help us reason under conditions of uncertainty. So a person who has had the opportunity to examine the coin and who can tell that maybe it seems weighted in favor of heads, they should rationally assign a different probability to the proposition that the next toss of the coin will come up heads as compared to someone else who has not had the opportunity to hold and examine and feel that coin. Okay. So in a Bayesian context, people who have different information rationally should be assigning different probabilities. So probability is not an objective property of the world. It is our view about the likelihood of something of interest given the information that we possess. I should just say here that in some situations, Bayesian probabilities can also be identified with proportions, or they can be approximated as proportions. But in many contexts, we're not going to be working with proportions at all, and probabilities are simply going to be the degree of belief that we hold in a proposition given the relevant information that we possess. Bayesian probability has a lot of great advantages. So first of all, it allows us to directly ask the kind of question that's usually of most interest, which is how plausible is the hypothesis given the evidence? So if you have had exposure to frequentist statistics, you'll know that in that framework, you're not even allowed to talk about the probability that a hypothesis is true. So things get much more complicated right off the bat. Bayesianism is well suited for explaining unique events or for working with a small number of cases. So we're getting into some of the things that are especially important for qualitative research. It's going to allow us to use data that cannot naturally be considered to come out of some kind of stochastic process, some process that you can model as the flip of a coin or the roll of dice. Another really nice advantage of Bayesianism is that it's going to apply the same fundamental inferential logic to all types of data, whether qualitative or quantitative. So in that sense, it can really serve as a bridge between qualitative and quantitative research. And many of us will argue that Bayesian probability is much more intuitive. It's much closer to how you think about probability in your everyday lives. So I put up this quote here from Laplace, who says that Bayesian probability is common sense reduced to calculation. So it's got a real nice intuitive sort of background here. Okay, got a question in the chat here. Can I consider Bayesian probability to be more advantageous than frequentist probability for understanding social phenomenon, or should we choose between the two categories depending on the specific research question? Okay, so I'm going to advocate for being Bayesian all the time, right? What I'm teaching you in this session is about how to apply Bayesian principles to analyze qualitative information. You cannot apply frequentist statistics to qualitative information because by its own sort of foundational principles, orthodox frequentist statistics requires stochastic data. So the minute you're working with, say you're doing interviews with expert informants or something like that, the minute that you have that kind of non-stochastic information, you cannot apply frequentist statistics. So we're talking about a realm where you absolutely must, in my view, apply Bayesian probability. Now, people use frequentist statistics all the time for large and quantitative research. Bayesian statistics works perfectly well and arguably much better there also. So you can always use Bayesian probability. But I mean, certainly in my field, we have a lot of so-called multi-method research where people will do frequentist statistics for some large and cross-case data set. Then they'll use some other framework to try to do analysis of some case studies. You can use Bayesianism to do all of that, but then of course you've got to learn Bayesian statistics, and Statistical Horizons has several workshops coming up on Bayesian statistics. So I would flag those for you as well. I'm going to be sitting on those too. Okay. Okay, so mathematically, we are going to use the notation of conditional probability to express our degree of belief in a proposition given whatever relevant information we have. So this is, if you haven't seen this notation or not for a while, let me just make sure that this is clear. So here we have the probability of some proposition A given information I. So this is expressing how confident we are that proposition A is true in light of information A, or given information, excuse me, in light of information I, or given information I. So in a Bayesian framework, all probabilities are conditional probabilities like this, right? So again, P just stands for probability. We're asking about the probability that the proposition that shows up to the left of the vertical bar is true, given or conditional on or considering everything that comes to the right of the vertical bar to be true. Okay. Let's come back now to our two chocolate boxes. Here is the first version of the problem. We've got our candy store making milk chocolate and dark chocolate. We have the two boxes left at the end of the day. In this context, the owner tells us the box on the left has dark chocolate. Our question is, what is the probability that both of the boxes contain dark chocolate? So what we're asking here, we're asking, what is the probability that this proposition A, both have dark chocolate, is true, given this relevant information that the owner has shared with us, which is that the box on the left has dark chocolate. So what is the probability of A given I? What is the probability that both of these candy boxes have dark chocolate if we know that the box on the left has dark chocolate? Okay. So I'm going to give you just a couple minutes here. I'll start my timer to choose see if you can figure this out. I've given you some multiple choice on the right. So take a minute, jot down, you have a think, and jot down your answer. Okay, so I see that most of you have typed answers into the chat, which is great, super helpful. Before we talk about this version of the problem, I want to show you or remind you the second version of the problem and give you a think on that as well. Okay, so let's go to the second version of the problem. So here we're interested again in the same proposition. We're interested in the probability that both have dark chocolate, but now we have different information. The owner has told us in this instance, I looked in one of the boxes and I saw that it had dark chocolate, but I don't remember which one of those boxes it was. Okay, so have a think about this. Take a couple minutes to jot down your answer. Okay, so the second version of the problem is harder. you were slower to put your answers in, and we've got a lot more spread. And that's what always happens with these two problems, which makes them really great and really interesting and fun. So let's go through this together. So you all got the answer right for the first one. Well done. So in this version of the problem, again, we know that the box on the left has dark chocolate. So that information restricts the possibilities to two. So we know that either this box on the left has dark chocolate and the box on the right has milk chocolate, or the box on the left has dark chocolate and the box on the right also has dark chocolate. So we're looking at just two possibilities here. And in the absence of sort of any other salient information, we would just assume that each of these possibilities is equally likely. So we come out with 1/2. So y'all did real well on that. Now, we can deal with the second problem here in the same way. So this is the harder problem, but the idea is the same. If we know that at least one of the boxes has dark chocolate, then basically we're looking at 3 possibilities. So it could be that we have dark on the left and milk on the right. We could have both dark, or we could have milk on the left and dark on the right, okay? So here the information that we're conditioning on restricts us to these three different possibilities. And again, in the absence of any other salient information, we would assume that these possibilities are all equally likely, and that leaves us with a probability of just 1 out of 3 that both of these boxes will have dark chocolate. Okay. So this is tricky, and it highlights, I do this problem to highlight that sort of differences in the information that you're conditioning on matter for the probabilities that you assign. And thanks to sort of the nuances of the English language, sort of differences in the information that may not seem on the surface like they make a big difference could in fact make a big difference. So learning that one of the boxes has dark chocolate, but not remembering whether it's the one on the right or the one on the left, actually puts us in a very different context than knowing that the one on the left has dark chocolate. So it can be a little counterintuitive. But if we just, again, in this problem, consider the possibilities that are consistent with that knowledge, then we will come out with the right probability here. Okay, a couple questions. What if the shop owner misremembered? Okay, so that takes us to what I'm going to call testimonial evidence, when we are getting information from sources that may not be truthful or may not be accurate. We will talk about that in the course of the next day or two. Okay, we will come to that. And Douglas asks, that feels like a frequentist approach to the problem. Is that a misinterpretation? Well, the main point here, again, is that, I mean, I don't think a frequentist would disagree with how to solve this problem, but the point that we're making right now is simply that we're always going to be working with conditional probabilities, and that if you're conditioning on different information, you should assign different probabilities. So we're not quite in the realm where like a frequentist and a Bayesian would do things differently yet. But this is just to sort of get you used to the idea that not just in this context, but much more broadly, we're going to be taking probabilities as our rational degree of belief given the information that we have. Okay. So different information, different probabilities. Okay. Let me see, it looks like I have one more. Okay, that makes sense. Okay, super great. Excellent, excellent. All righty, so moving forward, now I've given a little introduction there to conditional probability. There are two basic rules of probability that I'd like you to be familiar with. We have the sum rule and the product rule. Okay, so the sum rule says that the probability of any proposition and the probability of its logical negation, which I've denoted with that little squiggle. So this means not A, or A is false, A is true, A is false. So the sum of these two probabilities must add to 1. And this is just a generalization of the logical fact that A must either be true or false. Okay. So if A is the proposition that it's going to rain on Monday afternoon, then whatever information we have from looking out the window in the morning, we know for sure that the probability that it will rain plus the probability that it will not rain is going to equal 1. Okay. Okay. Then we have the product rule. So the probability, here we have the probability that both A and B are true given some information I, is going to equal the probability that A is true, the probability of A alone, given that information I, multiplied by the probability of B, given A and I. Okay. So why is this useful? Well, let me give you a little example. So suppose that A is the proposition that the Democrats win the presidency in the 2024 elections. B is legislation to reduce carbon emissions. And our background information is that the urban vote is underweighted due to electoral rules that favor small rural states in the electoral college. Okay. So if we are interested in the probability of both Democrats retaining control and legislation to reduce carbon emissions, we can first evaluate the probability of Democrats winning, given that the urban vote is underweighted. And then we can assess the probability of carbon emission legislation if the Democrats do, in fact, win the presidency. So breaking it down like this is going to make it easier to think through the joint probability of both A and B. Okay, so starting with the product rule, it then just takes a few steps to derive Bayes' rule. Bayes' rule actually just follows directly from the product rule of probability. All we need to do is substitute a hypothesis H for proposition A and substitute evidence E for proposition B, and just do a little bit of rearranging. So you can try that on your own if you'd like. And the main takeaway point here is just that Bayes' rule is a fundamental rule of probability. And this is what we're going to use to guide our reasoning about how to update our probabilities when we learn new information. Okay. So if you're familiar with Bayes' rule, if you've seen this before, this is probably the version that you've seen before. We're not going to use this version. I'm going to show you a simpler form that gets rid of this kind of pesky term in the denominator. And that is the relative odds version of Bayes' rule, which we get by just taking the ratio of Bayes' rule for H1 and Bayes' rule for H2. You can try that on your own as well. And the fundamental motivation for doing this is that inference essentially always involves comparing hypotheses. Okay. So what do we have here? Well, Bayes' rule tells us that the posterior odds equal the prior odds multiplied by the likelihood ratio. Here are the corresponding sort of mathematical terms below the names here. So on the left side, we have our posterior odds in favor of hypothesis 1 relative to some rival hypothesis 2, in light of or given all of the information that we know at the end of our research, including whatever evidence we've gathered and whatever relevant background knowledge we started out with. So Bayes' rule tells us that the posterior odds equal the prior odds multiplied by the likelihood ratio. So the prior odds here, this is our sort of initial view about which hypothesis is more plausible in light of our background knowledge alone. So what are the odds on H1 versus H2, considering only the background knowledge? And then here we have the likelihood ratio term. This is sometimes called the Bayes factor for quantitative folks. So here we're asking what is the likelihood of the evidence if H1 is true relative to the likelihood of that evidence if H2 is true. Okay. So here we're basically sort of imagining a hypothetical world where H1 is in fact true. We don't know. I mean, what we're interested in at the end of the day is how likely it is that H1 versus H2 is true. But when we're evaluating this term, we're going to assume for the time being that H1 is true and ask, well, how likely would the evidence E be if in fact H1 is true? And then we're going to say, well, suppose instead that this other hypothesis is actually true. How expected would the evidence be? Okay. So this is going to be our key inferential step that tells us how to update our odds. So whatever our prior odds were, we're going to gain more confidence in whichever one of these hypotheses makes our evidence more expected. That's going to be how we get from our prior odds to our posterior odds. The evidence will favor whichever of these hypotheses makes it more likely or more expected. And I will say much, much more about this as we move forward. Okay. So this is it. These are all of the basic mechanics that we're going to need. Probability represents the rational degree of belief that we should hold in a proposition given a particular state of information and any assumptions that we need to make just to define the problem. And Bayes' rule governs how we should update our views about which hypothesis is more plausible in light of the evidence that we learn. Okay. I see a question here in the chat. So we need to place a bet between the likelihood of the evidence given H1 or the likelihood of the evidence given H2. Yeah, I mean, I think that the betting language is a little bit more commonly used with regard to the posterior odds on the hypotheses or the prior odds on the hypotheses, but either way, we're evaluating relative likelihoods here, right? So this is the relative likelihood form or the odds ratio form of Bayes' rule. And yes, I mean, we are evaluating the probability of the evidence in the world of one hypothesis relative to the probability of the evidence in the other world. But again, I think that that language about betting, are you more, if you think about your prior odds, like from the outset, are you willing to place more money on H1 versus H2? How much more money, et cetera? That would be sort of a more common language for talking about the prior odds. Okay, good. Let us go to this example to just get a taste for working with Bayesian probability. So here we have a crime scene problem. So the police have figured out that two people carried out a crime. Each one of the people involved in that crime left traces of their blood at the scene. And the blood types that we have are O, which is a common type that's found in about 60% of the local population, and AB, which is a more rare blood type with a frequency of 1% in the local population. The police have one suspect in custody. That suspect is tested. We find out that they have type O blood. And the question is, does this evidence, does the fact that the suspect has type O blood, does that favor hypothesis 1, that this suspect participated in the crime? Or does it favor the rival hypothesis H2, which says that the suspect is innocent? So two as yet unidentified people were plotting that crime. Okay. So just have a quick think about that. This is actually a fairly hard one for our intuition, but Bayes is of course going to help us solve it. So anytime your intuition is sort of strained with one of these probability questions, if you sit down and apply Bayesian probability, you will come out with the right answer. So it's very helpful, very useful. Okay. So here, this is the same problem. I've just broken it down into all of the components that we need to be able to basically apply Bayes' rule. So all of this information is basically, I'm going to take this as background knowledge, background information that sort of structures the problem. So we have the two people that carried out the crime. We know the frequencies of each blood type in the local population, etc. We have the suspect in custody. The evidence that we're going to evaluate, that suspect has type O blood. Here are our two rival hypotheses. And our question is, does this evidence favor hypothesis 1 or hypothesis 2? Okay. So the question that I'm asking you here is really just to evaluate the likelihood ratio. So we're just going to completely ignore the prior odds right now. We're just not going to worry about that. The question is simply, does the evidence favor H1 over H2? And remember that it's this term evaluating the relative likelihood of the evidence in the world of the first hypothesis relative to its likelihood in the world of the second hypothesis. This is what tells us whether the evidence favors H1 or whether the evidence favors H2 and how much. So let me take you through this one, and then I'll give you another version to practice. So let's start with the first, right, so we need to evaluate these two terms, okay? So if the suspect participated in the crime, then given our background information, okay, we're going to start with evaluating the likelihood of the evidence in the world of the first hypothesis. So given the background information, their blood type has to be either O or AB. Those are the only two possibilities. So the probability that our suspect is the one who has the type O blood rather than the type AB blood, that's going to be 1/2. Okay, so again, if we're assuming that in fact this hypothesis is true and the suspect did participate in the crime, they can have type O blood or type E blood. Those are the only two possibilities. And in the absence of any other information, we would just say, okay, well, it's equally likely that they would be the person with the O versus the AB. Does that make sense? Check the chat. This is the trickiest part. It's evaluating that first likelihood term. I think that is the trickiest part here. Okay. And then if we evaluate the likelihood of the evidence under H2, okay, so here, if the suspect did not participate in the crime, then the samples found at the scene just give no relevant information at all about the suspect's blood type. So then we have to look to our background information, which gives us the relative frequencies in the local population. So the probability that S is type O is just the same as the prevalence of that type in the local population, which is going to be 60%. So it's really the background knowledge here that is driving the probability of the evidence in the H2 world, because H2 doesn't tell us anything relevant about the blood type. Okay. Does that make sense? Okay. So now we have everything we need, and we're just looking for the ratio of those two. Here's our likelihood ratio. It's 5-6. So this evidence actually ends up favoring the hypothesis in the denominator that the suspect is innocent and two as yet unidentified people carried out the crime. Okay. So I don't know about your intuition, but I find this pretty counterintuitive, or certainly before I started working with Bayes rule. But this is a great example to highlight a really important Bayesian point, which is that evidence that is consistent with your hypothesis does not necessarily support your hypothesis. And I'll say this many, many times. This is just a key insight that's really, really important, especially when we start working with qualitative research. So evidence can be perfectly consistent. Well, I shouldn't say it that way. Evidence that is consistent, that seems to fit with your hypothesis, does not necessarily support your hypothesis. You've got to evaluate how likely that evidence is in the world of the rival hypothesis before you can come to any conclusion about which hypothesis the evidence favors. Okay, I've got a question about the 0.6. So sure, let me go back through the 0.6. So the likelihood of the evidence under hypothesis H2, or this likelihood here we're asking, how likely, or what is the probability that the suspect has type O blood if hypothesis H2 is true, which basically says that suspect S is innocent. They were just at the wrong place at the wrong time when the police came through and gathered people up, but they did not participate in the crime. So how probable is it that an innocent person's blood type will be O? Well, we have to look to our background information here. This is just some innocent person from the local population who got caught up by the police. And our background information tells us that type O is 60%. The prevalence is 60% in the local population. Did that help? Is that more clear? Okay, excellent, great. Any other questions on this? And a question to go back through the 0.5, yes, absolutely. So that's the one that I think is more difficult. Here we're saying what is the probability that the suspect does indeed have type O blood if the suspect is guilty, so to speak? Well, if the suspect is guilty, again, we know from our background information that one of the people who committed the crime has type O, one of the people who committed the crime has type AB. Okay. So we have one of those two people in custody. We have one of the two people who actually committed the crime in custody. So their type has to be AB or O. So what's the probability that, the suspect that we have in custody is the one who has the type O blood? Well, it's just one half, right? The only other possibility is AB, and well, we just happen to grab the person who has the type O blood. Did that help? Was that more clear? Okay, great, great, great. All right, so let me now show you a different version of the problem. And this one I am going to give you a little time to try to work through on your own. So now suppose that the suspect is found to have type AB blood. Okay, so same setup, different evidence. The evidence is that the blood type of the person in custody turns out to be AB. So see if you can go through, evaluate the likelihood of the evidence if H1 is true, evaluate the likelihood of the evidence if H2 is true, and compare those to figure out which hypothesis this evidence supports. Okay, so thanks to everyone for taking a stab at this, and we got some good responses here in the chat. Let me just say right now, if you like these little probability problems and you're having a lot of fun with it, that's great. If you don't like them, don't worry. All right. As soon as we're done with this section, which is almost right now, you're never going to see this kind of setup again. We're going to go into a more social science kind of context. So if you don't like these little problems that we're doing right now, you'll never see them again, and that will be okay. Okay, so Douglas and Kim put in very nice answers to this in the chat, and I'm just going to walk through. It's the same kind of reasoning that we used before. So if we start out evaluating the likelihood of the evidence in a world where H1 is true and our suspect did participate in the crime, so nothing is really different here. It's just that now we happen to net the suspect with the type AB blood rather than the suspect who has the type O blood. But it's the same idea where if we know, if this hypothesis is true that this person participated in the crime, we know for sure that their blood is either A or AB, and it's just a toss-up that it's the AB rather than the O. Then for the likelihood of the evidence, if hypothesis is 2 is true and our suspect is innocent, well, then we just have some poor person who accidentally got arrested by the police, even though they're innocent. Their blood type is AB. Well, they're just some poor person from the local population. And we know that AB has a frequency of 1%. Okay, so this likelihood is 1%, whereas it was 60% in the previous problem. And now we can see that we get very different evidentiary support here. So now we have evidence that weighs pretty strongly in favor of the suspect's guilt, right? So the likelihood is much larger if hypothesis 1 is true relative to hypothesis 2. So that is going to mean we have evidence that pretty strongly favors H1 relative to H2. Does that make sense? Again, the evidence favors whichever hypothesis makes it more likely, more expected, higher probability. Those are all sort of synonyms. And this evidence is much more probable, much more expected, much more likely in a world where the suspect is in fact, guilty. Let me see the chat here. Thumbs up. Okay, all good. I like that. I've got thumbs up in the chat. Excellent, folks. Okay. So here's the review of what we've done so far. Well, I've introduced you to some basic Bayesian conditional probability, Bayes rule. These are the tools that we're going to use moving forward. And now we're all set to sort of jump into this process and apply it more broadly